All right, everybody. 4 o'clock, straight up, starting the stream. Hello and welcome. We'll start here in about 5 minutes. Got a good one for you today. You guys are really going to like this. They've all been good, but you'll see. All about the models.
Hi, I'm Kara, and I love making love.
Oops.
And I hate my period.
I don't know why my the monetization for my stream is I turned it off, but it's just I can't make it. I don't want it monetized because I'm supported by Patreon. So and whatever I do, I can't turn the stinking pre-roll. So that was a great one. That's all right. Whatever. Share. Yeah, I got to dig into my YouTube channel and figure out how to turn off monetization. There's got to be some layer that I'm missing. But anyhow, whatever. When people tune in and see the playback, they'll be like, what the heck? Hello. We're getting there, posting the link everywhere. Facebook. And I should know this, Jack, but is it weathermodels.com or .us?
Weathermodels.com and weather.us.
Right. All right, thanks.
Yeah.
Appreciate
and
it.
Weather.us is free, so you don't need a subscription or anything to look at all the stuff on there. And
right.
If you want some more of the bells and whistles, then the subscription portal is Weather Models.
All right. Almost ready.
I'm ready to hit the retweet button when I see it pop up on your feed here.
There we go.
All right.
I'm going to grab a charger for the iPad. It's trying to drain quick. Got a perfect track record so far of no technical difficulties. Knock on wood.
All right.
Not going to start today. All right, power supply. These things are, let's see, is my camera off? Let's see. Come on. There we go, camera on. These things right here, it's a company called Anchor.
Oh yeah, I have several of those.
Yeah, they're the best.
Yep.
We got the real.
I got mine right here.
Yeah, there you go. Yeah, these are 26,800 milliamps or something like that, or 28.6.
Wow.
And,
Yeah.
and then we have 50,000 milliamp hour ones that power our unmanned cameras. And
Oh yeah.
I think I've got 36 of them or something like that.
Wow. That's spectacular.
Not cameras, but batteries to power the 15 cameras.
Wow. That's a lot.
So I better have enough portable power to keep my iPad going during a broadcast. That's the way I look at it. No excuses. All right, come on, iPad. Let's give it a little bit more volume. All right, everybody, thanks for joining in. We're going to start here in just a moment. I promise. As I figure out all this.
Chili, in your spot.
All right. Well, it's 7 minutes after 4, so let's get started, shall we?
All right.
All right. Well, good afternoon, everybody. Mark Sutton of HurricaneTrack.com here, and welcome to another live broadcast of Hurricane U. Today, we're going to talk all about hurricane models and numerical weather prediction and how all of that relates into what we do when we track hurricanes. I think this is going to be very fascinating. We're just building on each one of these live broadcasts. Last week, we had Ben Knoll, and today I welcome Jack Sillen. And we're going to talk all about, at least as much as we can cram into this time frame here, computer models, how they do what they do, what you should take away from them. When you look at all of the stuff out there, you hear these terms like spaghetti models, ensembles, you name it. You've seen it. There's a lot of noise out there. And I'm very proud to have somebody who can help us decipher and break the code of some of that noise anyway. My guest today, let's bring him up on the iPad here. And by the way, this is being broadcast, as always, from my daughter's bedroom in Wilmington, North Carolina. She's a college student at UNCW, and so she lives here. We live 2 miles from the campus, if that, so wasn't going to pay for a dormitory just yet. So she lives at home. She's got a 65-inch Samsung high-def television that I have taken over so that my guests can appear at least as close to life-size as possible. So thank you to my daughter Mallory for the 4th week in a row for abandoning the premises so that I could do this. All right. Also a college student, believe it or not, this guy is a college student and he is kicking rear end on social media with his job working with the weather model site and weather.us. I want to welcome all the way up from Maine, where it's chilly today, Jack Sillen. He's our guest as we talk about computer models. Jack, welcome to today's Hurricane U.
Thanks so much, Mark, for having me and for giving me the opportunity to talk weather models with all of those who are watching.
Oh, absolutely. I'm very excited about it. I know that the audience is going to learn a lot. Computer models are a big part of the whole hurricane wheel that goes into motion. So before we get into the nitty-gritty here, tell us a little bit about you. It says on your Twitter bio. I think you're the class of 2022 from Cornell. That's amazing that you do all of this. You're a student. You're also running what you do with the weather models. So Jack, take it away. Tell us about yourself a little bit. Hobbies, why you got into this, your love of weather, and what you plan to do once you graduate.
Yeah, so I've been interested in weather since I was a little kid. We had a big nor'easter, as we call them up here in Maine, that caused some severe damage near my house when I was about 6 years old, and that really got me going on the path of meteorology, which I've been studying informally all throughout middle school and high school, learning about how the atmosphere works, how these computer models work, and how to use them properly. And then I'm now lucky enough to be able to study the atmosphere formally. I'm an atmospheric science major down at Cornell, and I'll be this is nearing the end of my second year there.
Wow.
So really, yeah, it's been a lot of fun. It's been very hard. You gotta take a lot of math and science classes to be an atmospheric science major. So definitely have been brushing up on my calculus and my differential equations alongside my map analysis in tropical meteorology. So that's been a lot of fun. My heart is really in the operational forecasting side of the field. I have a ton of respect for the folks in research, but my goal one day is to be on the operations desk making forecasts for whoever needs them. So that's a little bit about me, where I've been, where I'm hoping to go, and I'm really excited to be here.
Well, I appreciate that. That is quite a remarkable resume so far. You talk about brushing up on calculus and brushing up on differential equations. I made sure I avoided all of that. When I do a book someday, I think the real story will come out as how I got into this. I studied geography. I was going to go into meteorology. I was accepted at NC State University. I was thinking about going to Mississippi State, maybe getting into broadcast meteorology. And so the story that I go with is that I met a girl here in Wilmington, and I wasn't going to leave. She's now my wife. So I was like, well, sorry, UNCW doesn't have meteorology, so we'll just do geography instead. And so I got a free pass that I didn't have to study differential equations or calculus, but I still got to study hurricanes as part of my geography curriculum. And, I don't have the degree in meteorology, but you know what I mean? It's kind of like being a PA versus a doctor. Still very, very important, but not quite the same as that MD. But I did get to skip the old calculus and differential equations. Thank goodness, because it sounds rough. That's for sure.
Yeah, it has its moments, that's for sure.
Absolutely. All right, so let's transition and jump in both feet at the same time, as it were, with what are numerical weather prediction models? And I got the graphic up here of what is a model. So Jack, talk us through that, please, on the very basic level. What are we talking about when we talk about numerical weather prediction and computer models?
Yeah, so numerical weather prediction is a method of trying to predict the future state of the atmosphere, right? So that's what we're talking about. What is the sort of end goal of our jobs as forecasters? Both folks like me who do this on a sort of social media level, folks like you who are looking, where you're going to try to intercept the storm to measure it and document it on the ground. Folks like the Hurricane Center who are protecting lives and property. With their forecasts, we're all trying to figure out what the atmosphere is going to do at some future time. And the roadmap for how we get there from the numerical modeling side is we have to first gather a whole bunch of data about what the weather is doing, what the atmosphere is doing at this particular moment. So that's the first step. We need to know what's happening now. If we don't know what's happening now, we have absolutely no idea what's going to happen in the future.
Right.
So that's the first step, and I'll show you a really neat animation of how that works in a second. The second step is that we then are going to run and solve all those differential equations that I'm learning about. We actually teach a computer model how to run those and solve those for millions of grid points, instantaneous spots all around the Earth's atmosphere. And then the solutions to those differential equations, that's our weather. It's in a little bit coded form, right? So you need to decipher, these models spit out, long lists of letters and numbers that are sort of meaningless. Even if I were to look at the raw data file, I couldn't tell you what the forecast was going to be. So then we develop these maps, and sort of that's what we do at Weather Models and weather.us is we turn those strings of letters and numbers into maps that can be then interpreted by forecasters or by people like you or by enthusiasts, anyone who's watching. This isn't top secret classified information. All those maps and stuff are out there for everyone to see. So if you're interested, take a look either at our websites or one of your favorites. So yeah, that's the basic roadmap. If you want to pull up the animation of the weather data ingest, this is really fascinating because it gives a little bit of perspective as to just how complicated that first step is. So each point that you see on the map on the TV screen there is an observation that's going into one single weather model run. So these models are run 6 times a day, most of them, and each one of those runs you have to ingest all of this data, and it's a ton. We get satellite information, we get information from airplanes, we get information from sensors on the ground, from radio songs. Yeah, so it's a whole lot that goes into it.
Yeah, let me see if I can get this to play again because I tried to be cute and pinch zoom and it upset the MP4 file and whatever.
Oh no.
That's all right. It's a really neat animation. So all those data points, you have upper air with the weather balloons. I think people are familiar with the whole idea of weather balloons. And we talked about the airplanes. So even commercial airliners, of course, right now with this pandemic, a lot of them are grounded, but how do the commercial airlines contribute to numeric weather prediction? I think that's fascinating as I try to restart that animation.
Yeah, it's actually, it's a staggering amount of data. Actually, around 9% of all the data that goes into these models come from commercial airliners.
Wow.
And there's actually been a measurable decline in skill over the past few weeks as so many of those flights have been grounded as a result of the coronavirus situation. So, yeah, it's a crucial part of the puzzle. And how they do that is there are thermometers, temperature sensors, and dew point sensors that every single aircraft is equipped with. The reason that they have these sensors is that they're worried about icing on the wings. So if the temperature is cold enough and if there's enough moisture, they need to employ certain de-icing protocols, or they may need to fly at a slightly different elevation or altitude rather. They may need to adjust their flight plans so that the wings don't get weighed down with ice. So that's why they have the thermometers, and of course, as meteorologists, we're interested in data from the upper atmosphere. It's relatively sparse. You can see that these radio songs are only launched twice a day. Satellites obviously only give us so much information about the vertical structure of the atmosphere. So given that these planes already have the thermometers, we combine that with their GPS information, and we're able to put together some 3-dimensional profiles of how the atmosphere is changing in time and space, not just in 2 dimensions, but also in 3 dimensions. So it's a critically important part of the puzzle. They also give us wind data based on how much fuel they need to expend to travel a certain ground speed. We can calculate what the wind speed and direction is. So that's another important part of the puzzle there.
So how does this data get input into the global model system, for the lack of a better term, seeing that it has to be coordinated around the world? How on earth is that done? It's not people emailing files like an attachment. It's got to be automated, I would hope, right? Generally.
Yeah. So that's the job of the World Meteorological Organization. Is the entity that is in charge of the international coordination. So from a practical standpoint, how that coordination gets done is dependent on the type of observation, right? So a long time ago, we set the standard times for observation at upper air sites to be 12 noon in Greenwich, England, and midnight in Greenwich, England. So everyone in the entire world launches their weather balloons. The data is uploaded to servers. I'm not sure exactly the technical procedure, but that data goes up into the cloud somewhere. where it's
Literally.
accessible for as input files basically to these models. So the models know where to look for these upper air files. They go and grab them. There's a computer program that's run to do that. The surface observations follow a similar format. Most of the surface stations nowadays are automated. So every time that sensor takes a measurement out at your local airport, your local observing site, it goes onto a server somewhere on a computer somewhere, and then the computer program that is running the model knows to go to computer X and file Y, and there we'll find the temperatures, say, in Wilmington, North Carolina for the past 24 hours. And then the satellite files, it follows a similar protocol.
Right.
So it's a lot of computer programming to get that to work smoothly.
And so to summarize, then, we have two main times, the synoptic times of 0Z and 12Z. We refer to that a lot. The 0Z GFS was initialized at 0Z, whatever. That's what that means. 12Z, we roughly equate that during hurricane season to 8 a.m. Eastern time. And it varies, but that's why UTC, or Universal Time Coordinate, it's a universal time. So you just say it's 0Z or it's at 12Z. Then sometimes more balloons are launched in between these runs to add a little bit more data. So quickly, why, or as quick as you want, I mean, I could be here all day. I think this is fascinating. Why is more data helpful? And I know that sounds like, well, come on, Mark, the more data, the better. But it really is more than just filling in the holes. We just don't have that much data to begin with. So even a few extra balloon launches, I guess, makes a difference. Otherwise, we wouldn't do it.
Yeah, so there are a few answers to that question because the value of additional data comes in several different flavors, quote unquote. So one benefit that we get out of more data is that it's easier to spot outliers. So sometimes, for whatever reason, there's a faulty sensor somewhere, and you get a bad measurement. The radiosonde malfunctions. So that's the instrument attached to the weather balloon is known as a radiosonde. Mm-hmm. Sometimes it'll malfunction. It'll give you a bad reading. But how do you know what's a bad reading and what's not a bad reading? Well, you can make a good guess. You can do your educated guessing, and there are extremely elaborate systems that are put in place, especially by the European Center. The ECMWF has some pretty phenomenal tools to pick out bad data before it gets into the model. But another way is just to add more direct observations, and then if one doesn't fit the pattern by a certain amount and there's no physical explanation for it, then it becomes easier to discard those bad observations. The second comes down to this idea of chaos theory, and you hear that a lot, and there's actually a really great illustration of that that's associated with Hurricane Dorian. So if we could pull up I think the graphic is called the butterfly effect. That'll be a good talking point here as we talk about a little bit about chaos theory and why it wreaks havoc on our weather prediction efforts.
Is it the one with the thunderstorms? It says forecast before thunderstorms started. Excellent, got it.
Yeah, here it is. All right, so this is obviously a high-profile tropical cyclone forecast. It's very important to figure out where Dorian is going to go, where it's going to make its northward turn. We're taking all these extra observations, right, because the extent to which Dorian is going to turn is going to be dependent on the exact strength of a mid-level area of high pressure over the Carolinas in the Western Atlantic. So we need to know what's going to influence the strength of that ridge in the Western Atlantic. And how strong it's going to be. So one way to figure that out is to just measure it, right, and see how strong it is. But the other thing that's really important is we need to measure any entities or disturbances in the atmosphere that may weaken that ridge at some point in the future. And that's where these thunderstorms over Kansas City come in. When those thunderstorms began to develop and intensify over Kansas, they added a whole ton of energy to the upper atmosphere. And that energy happened to coalesce into this upper level disturbance that I've circled in pink in the frames, the next frame over to the right. So those are the thunderstorms right there, and then I've circled, this is the model forecast before the thunderstorm started, and you can see there's that little dip that represents a very subtle upper level disturbance. And then if you slide to the next one over, you'll notice that this is the new forecast after the thunderstorms had already started.
Right.
And you notice that that dip is a whole lot stronger.
Ah.
Now, in the grand scheme of things, it's not actually that much stronger, right? That difference is minuscule if you were to look at it in a purely physical perspective. But the reason that those observations of just how strong that disturbance was, exactly where it was tracking, how much those thunderstorms were influencing the weather pattern, it became crucial because you can see in the bottom images that the forecast that didn't include the thunderstorm observations showed Dorian blasting right into Miami. And the forecast that included the observations of the thunderstorms showed the correct forecast, which is that Dorian would stall just east of Miami and then make a sharp turn to the north. And that's indeed what happened. So a few extra observations of those thunderstorms over Kansas City, combined with that upper level disturbance, ended up resulting in the models being able to correctly forecast Dorian's northward turn several days ahead of time.
That is absolutely remarkable that cluster of thunderstorms, just a small blip, like you said, kind of chiseling in on the upper level pattern, was just enough to lead to it not going into Miami, but we didn't see that coming, I guess, days prior, because how could you? That's, it's small, but a giant outcome in that Miami did not have to suffer a Category 5 direct strike from Dorian. That is incredible.
Yeah, and that's one of the reasons that weather prediction is so hard, right? Is because in order to forecast the path of Dorian, you don't only have to forecast, how the storm itself is going to behave,
right.
But you have to be forecasting, clusters of thunderstorms over 1,000 miles away if you have any hope of getting that day 3 or day 4 forecast correct.
Right.
And that's where the upper level, the additional observations are so critical, right? Because, it's not even clear, it wasn't even clear as those thunderstorms were building that would be enough of a perturbation to completely shift the track of a Category 5 hurricane. We were only able to confirm that hunch once we launched more and more upper level observations with those weather balloons, and then we were able to see that indeed that ridge was weakening, that trough was coming in stronger than expected, and therefore we could adjust the forecast.
But sometimes the setup is fairly straightforward, like Hurricane Andrew 1992. It just came right on in. Obviously, that was a different era in terms of our data capabilities, computer modeling, and so forth. But there are times when it is fairly straightforward. And so in simplistic terms, why are some of those forecasts easier versus something like Dorian, which literally, I got a more gray hair up here because of Dorian, I assure you, a lot of people do. Some of them are a lot easier, even if they're on the same type of trajectory. Why is that the case?
So it comes down to the fact that we have higher confidence in some forecasts, we have lower confidence in others because, not all systems are sort of caught in between several different larger scale features. So let's take a look, for example, at Dorian. If we want to pull up the ECMWF Dorian graphic here, you can see that the system is sort of caught in a tug of war between not one, not two, but 3 different upper level entities. And that's really what made this forecast so hard. If there was one upper level ridge or upper level trough that was steering the storm, I think that's the H-Wharf Dorian. And I think there's another one that's the ECMWF Dorian that shows a sort of wider look at the pattern.
There we go.
See some of the upper level troughs and ridges.
Got it.
All right, yeah, there we go. So you see that there's this area of sort of blue on the map that's located over southeastern Canada, is moving into the Great Lakes. That's an upper level trough.
Right.
And that guy wants to pull Dorian north and then eventually northeast up towards Nova Scotia. That's the influence. It's pulling in that direction. Then you'll notice that there's this upper level ridge, this area of sort of yellowy color that's off to the storm's northeast. It extends roughly from Newfoundland down to Bermuda. And that is pushing the storm off to the west.
Right.
So that feature wants Dorian to go into Miami. Now, to make matters even more complicated, there's one more feature, and it's over sort of Missouri into Arkansas, and that wants to push Dorian south, and then west eventually into the Gulf of Mexico. Now the problem is that where Dorian was and just the way things worked out, those influences were almost equal, right?
Oh, gosh,
you basically have, and actually there was one more now that I'm remembering. There's one more entity. It's a very weak system in the Gulf of Mexico that's trying to pull Dorian sort of west and
little thing
south
right there.
West.
Yeah, so that little, gosh, that's amazing.
Just a tiny little blue dot.
Right.
Yeah, so if you think about, having some object that you're pulling in 4 different directions at roughly equal strength, where's it going to go?
Yeah.
And the answer is that all you have to do to move that thing is add, 0.01% to any one of those forces to upset the balance and send it off in one direction. So normally speaking, you either have all those 4 players that are pushing in the same direction, right? If every one of those features wanted Dorian to go north, then it's really easy for us as forecasters to say, all right, Dorian's going north because the trough wants it to go north, the ridge wants it to go north, everyone's in agreement, we're all happy. But in the case of Dorian, you have the trough wanting it to go north, the ridge wanting it to go west, and that really gets us confused, or at least it makes the forecast a whole lot harder and more susceptible to those small errors causing drastic changes in the forecast track.
So then it goes, I think, following logic, that the less amount of players on the field, so to speak, the more straightforward the forecast. If you only had 2 of these entities playing tug of war, so to speak, it's going to be a little bit more straightforward forecast. But even that can evolve into a situation where there are more players on the field, to use the sports analogy.
Yeah, for sure. And it also helps, if those 2 players are both playing on the same team and they're both going for the same goal, that's going to make the forecast a whole lot easier than if you have 2 players on opposing teams, or even worse in the case of Dorian, if you have 4 players on opposing teams. And not just, that, it would be as if you had 4 players trying to score in 4 different goals.
Yeah.
Right? So you can imagine how tough that is. Even if you could have 4 players on the field, but if they're all on the same team shooting for the same goal, you can have a fairly high confidence that's where the storm is going to end up.
All right, well, let's talk about, hopefully you guys are following this. This is fascinating. If you wanted to have a breakdown, one of the things I really like about Jack is he'll post marked up what we call annotated graphics, maps and so forth, that explains a lot of what he just said in one graphic. And I think that's amazing. A great use of what we call a thematic map. And so it's nice to be able to have him break things down here for us today in relatively plain English. I mean, I'm following what he's saying pretty easily, and it just makes a lot of sense. So let's get on, and we got a lot of other graphics to show you all. Operational versus ensembles. What exactly, when someone says, well, the operational GFS just showed whatever, what does that mean? We'll tackle that first. What's an operational model versus the ensembles? And we'll get into ensembles after that, of course.
Yeah, so the operational models are the models that I described right at the beginning of the show here. It's a computer program that takes a variety of observations as inputs. It runs these differential equations, it does all this math, and then it spits out this output that is the simulated future state of the atmosphere at some time of interest. So that sort of 3-step process, and I've really simplified it there. So if there's any of my friends who work in the numerical modeling and who are in charge of building these things, I apologize for not including all the various other steps, but those are really the most important, right? If we're trying to aim for a broader audience, you take the inputs, you do some math, and you get some outputs, and that output is your forecast.
Right.
But as we saw in the case of Dorian, very small changes in the initial conditions of the model can have drastic impacts on where that storm ends up at the end of the forecast period. And the problem is, if we think back to that loop of all the dots that are observations going into the models, if you remember, there are a lot of gaps. So even though there are a lot of dots, there are also a lot of holes where we're not observing the atmosphere in any meaningful capacity, and those holes exist both in time and space. So you could imagine that, even if we're able to see that thunderstorm complex over Kansas, we may not know exactly to what extent it is influencing the larger scale pattern, because we just don't have those observations. We need to wait a whole 6 or 12 hours for the next round of upper level balloon observations to go and find out exactly how strong that trough is, exactly how strong that ridge is. So one way we can solve that problem is just by running that model over and over again, but with slightly different guesses as to what the initial conditions are, right? So the ensemble approach would be akin to saying, all right, the ECMWF model is thinking that there's going to be a weak thunderstorm in Kansas, right? What happens, just for the sake of argument, if we put a strong thunderstorm over Kansas? What happens if we put no thunderstorm over Kansas? What happens if we put a super strong thunderstorm over Kansas? And you do that 50 times and you come up with the European ensemble system, right? They're running, and in fact, actually the Europeans have now taken it one step further. This is really impressive. There are also errors, and I haven't talked about this yet, but that sort of doing the math part, it turns out it's physically impossible to solve some of those equations. Trust me, I've tried, and people who are way smarter than I have tried to solve these equations. There are some of them that are mathematically unsolvable. So, think that through for a second. How weird is that?
Yeah.
We've reached the exact limits of what, not only we do understand, but what we're capable of understanding. So we have to make some educated guesses along the way, and we realize that those guesses aren't perfect. So the ensemble approach basically says we're going to take many different guesses about what the atmosphere is doing now, and then we're going to take many different guesses about how that atmosphere might evolve through time, and then we're going to get a range of possible outcomes. So each ensemble member represents a sort of what-if scenario.
Gotcha.
What if the thunderstorm over Kansas was a little stronger?
Right.
What if that trough was a little weaker? What if that ridge was a little farther west? And that gives you this range of possible outcomes that's extraordinarily valuable because it quantifies the uncertainty that you're not seeing in that operational forecast. The operational forecast is going to, sort of decisively say this is exactly where the storm is going to be 7 days from now, when it's really just one possible outcome of many. So that's really where the value in the ensemble approach comes in. And we can get a sense of what that looks like in real life if we go to the Dorian spaghetti. We'll start with the unannotated version just to see sort of, if you follow hurricanes, you've probably seen a map that looks something like this. This is the classic spaghetti plot. There it is. So each of these lines, each line represents one ensemble member's forecast for the track of the storm. And you can see that there's a range of possible outcomes several days out, right? The storm might end up, safely east of Florida by a couple hundred miles. The storm might end up making landfall, or the storm might end up, making landfall and then going into the Gulf of Mexico. So there's this whole range of possible outcomes, and the operational is only going to show you one of those possibilities, whereas the ensembles let you see not necessarily all of the possibilities, but at least a wider range of the possibilities.
50-something of them. By the way, for those of you just tuning in, we are speaking with Jack Sillen. He is one of the gurus, and that is a very appropriate word because to me he is a guru. Behind the weathermodels.com and weather.us, right? Sorry, there's too many weathers out there. And so Jack Sillen goes to Cornell. He's a college student, but man, this guy is just sharp. So a couple people on the YouTube chat were asking, who is this? Well, this is Jack Sillen, and at weathermodels.com, you see his blogs. They are fantastic. Follow him on Twitter. And these annotated graphics, which is what we're getting ready to lead into here, this is the guy that does those. I read them, and it helps me to make sense about what I talk about when I do my Hurricane Outlook and discussion videos. So we're all connected here. So that's who we're speaking with today. All right, so let me just ask you a couple things that came to mind. Why is it called the operational, whether it's the GFS, the Euro, or whatever? Who decides that the run that we see as the operational is the operational, if there's a way to answer that?
Yeah, so that comes down to the operational is what you get with our best guess, right? So we make our very best guess of what the atmosphere is doing right now. and our very best guess of how to solve those equations in the most sensible way possible, the most accurate way possible. And that is the single outcome. There are lots of folks who, for a variety of reasons, need a deterministic yes or no, this is what's going to happen forecast. And that is, if they want the best possible forecast, that is couched in those sort of deterministic terms, that's what you're going to get out of our best guess model. And that's why we call them the operational. If you're in operations and you need a single answer, this is the single best answer we can give you.
Perfect.
The ensembles are really a measure of sort of covering ourselves, right? So.
Right.
It's all right. We know that we're going to get this wrong. In case we get this wrong, how are we going to get it wrong? And then what would happen?
Right. What are some possible other things that could go wrong, kind of thing? All right. So now we've got the annotated, this awesome annotated. I remember this. I do. I remember sharing it with Brent and Tony, my colleagues. Poor Brent was pulling his hair out too. Story for another day. You'll see that on an upcoming Hurricane Highway. We'll talk about that later. But anyway, so I remember this when it came out, and I was just like, wow, that's a lot of stuff on there. That must mean it's complicated. The more you see Jack mark something up, the more complicated it is. I was like, all right, well, let's see what. So what are we looking at here? So let's let you continue.
Yeah, so this is what my mind's eye sees when I look at that spaghetti plot that we just looked at a minute ago. And that's really what I was trying to go for here is what am I looking at when I see this? So we're going to start just north of Puerto Rico. That's where the storm was located when this model run was initiated at 12Z, the 29th of August, 2019. And you notice that right near the beginning of the forecast period, all those lines are clustered very close together, right? They're all moving to the northwest. That indicates very high confidence in the forecast track. So that's all the models are all the ensemble members rather are in agreement. This is where the storm's going. We're happy as forecasters. So then the storm sort of enters the next phase of its evolution, and I've marked that out in the sort of darker red arrows. And that's the storm is going to make this turn to the west, and that's in the sort of 24-hour time period.
Right.
And now notice that all of the models are on the ensemble members rather are showing that turn, but they disagree a little bit about exactly where that turn's going to happen.
Sure.
Some of them have it turn a little bit more, which would indicate a track farther to the south. Others are waiting a little bit longer on the turn or making that turn not necessarily quite as sharply. So you can see I've now added two arrows that represent the sort of slow turn and the fast turn scenarios, right? So we're trying to build up to this range of possible outcomes, right? So one possible outcome is a slow turn, one possible outcome is a fast turn.
Yeah.
Now once we move into the next phase of the evolution, that's where I start to get into these purple arrows.
Right.
And one of these outcomes that at this point I was thinking was very unlikely but couldn't quite be ruled out, that's that track farther west into the Gulf.
Right.
I felt obligated to keep that in the mix because I wasn't necessarily ready to say you're all clear Alabama or you're all clear Mississippi or you're all clear Louisiana.
Right.
But that was looking like a lower probability event. What was much more likely is that the storm would then make some turn off to the north. And that's what those lighter purple arrows represent. That turn was going to happen on that Monday, I believe September 1st. But we didn't quite know where that was going to happen. And that's why I've now included 4 arrows, because we have roughly 4 different scenarios. One of which is that it turns north very quickly and there are minimal impacts in Florida. Mm-hmm. The second is that it turns north after moving west for a little while longer, in which case you'd have minor to moderate impacts in Florida. The third possible outcome is that it would turn right before it reached the Florida coast, in which case you'd have significant but perhaps not devastating impacts to Florida. And the last possible outcome is that it would turn north after it moved onshore and made landfall in the Florida Peninsula. So you notice that we've now been building in our arrow count, so to speak, right? We had 1 arrow in the first sort of chunk of the forecast. We were very confident. The second chunk of the forecast had 2 arrows. We're starting to have some questions. The third chunk of the forecast now has 5 arrows. We're building up the uncertainty because we're dealing with that tug of war sort of situation that we mentioned earlier. And then the last sort of phase of the storm's forecast is this turn off to the northeast. And all the ensemble members thought that this would happen eventually. Whether it happened over Alabama, that seemed pretty unlikely, but possible. Whether it happened over interior parts of sort of southeastern Georgia into central South Carolina,
Right.
that also seemed possible if the storm made landfall before it turned north. And then there are some other sort of possibilities that involve more of the South Carolina, North Carolina coastlines. And then eventually the storm is going to exit off into the North Atlantic, somewhere southeast of Cape Cod. So that we were very confident about. This isn't the kind of thing that's going to barrel into the Ohio Valley or up into New England. It's going to sort of skirt east, northeast at some point. So ironically, the most uncertain part of Dorian's forecast was not the part that was farthest away, right? You know, we were able to say confidently by day 7, this is going to be accelerating east-northeast towards Nova Scotia.
It's that in between.
We just don't know what's going to happen day 4, right before it gets there.
That's so. Think about what he just said. That the confidence later on down the road was higher than the confidence in the short term, which was where all the people were for the most part. Florida and points north. Obviously, the Bahamas were in the line of fire. But later on down, that's amazing. I never thought of it like that. How about that? All right, so we're talking about track forecasting. Where will a certain entity go? A depression, a storm, a hurricane? Where's it going to go? Everybody wants to know that, of course. But also, directly related to that, how strong will it be when it gets there? So now let's talk about intensity forecasting a little bit. That is not a completely different animal, but it's, where it goes is only part of the puzzle. So with intensity forecasting, that's another whole ball of wax, isn't it? So let's just go ahead and jump into that.
Yeah, so intensity forecasting, it turns out, is a whole heck of a lot harder than track forecasting. We've gotten steadily better with our track forecasts over the years, both on the modeling side and on the Hurricane Center side. But the intensity forecast, if you pull up the graphic, that's NHC intensity error. This is the historical plot of the Hurricane Center's forecast error with regards to intensity at various forecast times. And you can see that those lines are disappointingly flat, especially the 24-hour forecast line. We could tell you sort of plus or minus 10 knots what the storm would be 24 hours out back in 1990. And after, 30 years of innovation, we're now down to being able to tell you plus or minus 9 knots or so what the storm's intensity is going to be. So it's brutally hard. And the reason is that you have to simulate processes on a numerical modeling level and on the sort of forecasting level that are incredibly hard to do to predict intensity. And that's because the intensity of a storm is not just dependent on where it goes, but it's also dependent on these processes that are internal to a cyclone.
Right.
So if we pull up the HWRF forecast for Dorian, we can get a sense of that. So to predict the storm's track, right, you got to predict the location of these big upper-level high-pressure systems. Those are the ridges, and the big upper-level low-pressure systems. Those are the troughs. And we talked about some of the challenges associated with that, but our weather models are incredibly good at predicting where these ridges and troughs are going to be because they're huge, right? We remember that ridge extended from Newfoundland down to Bermuda. That's over 1,000 kilometers. That trough extended from James Bay in Canada down to Pennsylvania. That's well over 1,000 kilometers. Our models are really good at forecasting stuff on those scales, so we can do a pretty good job with the track. The problem comes down to when you need to simulate and forecast processes that occur on the scale of 10 kilometers or 20 kilometers. And that's where you got to figure out, is the storm going to ingest dry air from its environment?
Yep.
So this is what that HWRF simulation is showing here. Is this the storm is trying to pull in some of this drier air from Alabama and Georgia, but will it get all the way to the storm's inner core? And that's the question that we were trying to answer. You can see that there's this plume of dry air that comes from the Gulf of Mexico. It goes just south of Key West through the Bahamas, and then up and around towards Cape Canaveral. If that little plume of dry air was able to move through the eye wall, then the storm would weaken rapidly. But if that eye wall was able to fend off this dry air intrusion, then the storm would be able to continue holding its high-end intensity. Now, what determines whether that dry air is going to be able to make it into the eye wall or not? Well, it comes down to the mixing by turbulent eddies on the scale of maybe 10 to 50 meters, and the interaction of that dry air with water droplets that might be evaporating. So now we're talking, on the scale of a few millimeters, and our models absolutely have no idea what's going on at that level. Even the high resolution models, they have grid points every 3 kilometers.
Yeah.
So, you try to ask a model that has a data point every 3 kilometers to simulate a process that's occurring within 50 meters. Yeah, you're out of luck. So
wow.
That's why we really struggle with the intensity forecasts, both on the numerical modeling side and on the practical forecast side, because even the smartest forecasters who have been doing this for a long time and are highly trained at this stuff, they can't necessarily predict exactly which thunderstorm updraft is going to be shut off by evaporational cooling, whereas another one might not. So these are really small scale nitty gritty things that our models just aren't built to handle.
My power just blinked, which hopefully it won't do that again.
Oh no.
I jinxed it by saying earlier that we haven't had any technical difficulties. So let's see, we still there? Good. All right. Nervous. We've had a perfect track record so far. Sometimes intensity seems to play a role in track. Why is that?
Yeah, so that comes down to, remember we talked about that tug of war that was happening between these various mid to upper level features. And it turns out that there are, you can think of it as sort of rules about who's allowed to play tug of war with the hurricane. And which features in the mid to upper levels are allowed to play tug of war with the hurricane depends on how strong the hurricane is. So a stronger hurricane is fair game for features higher up in the atmosphere. So think about the jet stream, right? The jet stream is cruising along in the summertime in the northern hemisphere at about, in meteorology we talk in pressure coordinates. So it's usually 250 to 200 hectopascals, which I think translates to something around 45,000 feet.
Right.
We can look that up at some point later. But yeah, think 45,000 feet, the jet stream. That's only allowed to pull a hurricane that's Cat 3, Cat 4, or Cat 5. A tropical storm is going to have no idea from a steering perspective that jet stream exists.
Gotcha.
It's going to be completely clueless. And there are various other features, right? A mid-level ridge, such as that one that we were looking at between Nova Scotia and Bermuda, that's allowed to steer a storm as long as it's stronger than sort of a Cat 1 usually. And so, obviously Dorian was being steered by basically all available features. And that's another reason why the forecast was so hard, right? If this was a Category 1 or Category 2 storm, it would have been no-brainer into Miami, right? But it's only because it was strong enough to be pulled by that jet stream digging south over Quebec that it ever had a chance of going north. If you get a storm that was that's part of the reason why the forecast was so tricky for Dorian, right? We needed to know that storm was going to be a Category 5 to predict that it was going to turn north. And that wasn't always obvious, right? It wasn't always clear that the storm would be able to maximize its intensity to the extent that it did. And Dorian wasn't necessarily the prime example of track dependence on intensity. There are other storms that we could probably think of that were sort of more textbook cases of that. But yeah, it really comes down to which features on the synoptic scale or on the sort of hemispheric scale are allowed to tug the storm in different directions.
So one question, one of the graphics here has these SpaghettiOs, and this is what was driving my colleague Brent crazy. I kept talking about these different notions, thumb ridges, SpaghettiOs, and he's just like, dude, you're just making stuff up at this point. You guys are killing me. And he's come up to help, and it's like, what are you guys doing? So there's a lot of different ways to visualize the model output. And so I've got this one pulled up that shows and the theme of it is the along track spread and the ensemble guidance. But what's the deal with the SpaghettiOs and the spaghetti plots and what? I mean, I think the spaghetti plots make sense, but where'd you guys come up with SpaghettiOs?
Yeah, so the SpaghettiOs, that's a really cool, innovative way of looking at different types of forecast uncertainty. So the SpaghettiOs, you can think of, we're drawing isobar lines, right? So lines of constant pressure for each ensemble member at certain thresholds, right? So each green dashed line, the lightest green dashed line, is wherever an ensemble member has a closed load that's has a central pressure less than 1,000 hectopascals. And then we draw another line if it gets below, 980 hectopascals. We draw another line if it's below 970, 960, 950, so on and so forth. So this allows you to see, remember the other spaghetti plot showed you the entire model run's track. Right? But what if you only want to know where the storm is going to be at any one given time, right? It's not immediately clear. If I were to ask, where's the storm going to be on Monday, you wouldn't necessarily be able to tell me based on that spaghetti map. But you would be able to tell me basically by this instantaneous spaghetti map, I guess is one way of thinking of it, that shows you the location and strength of the hurricane as forecast by every ensemble member at some given time. And this allows us to distinguish between two types of uncertainty, right? And that the one is the uncertainty about the storm's forward motion. So that's known as this along track spread. And basically this reflects the idea that even if we know with perfect certainty where the storm is going to go, we don't necessarily know how fast it's going to get there. And this along track spread is a measure of quantifying that uncertainty. So you can see here on Monday 0Z, the 2nd of September 2019, which is when that plot is valid for, that storm, even if we were to say, I know it's going to follow this path along the black arrow, but it could be anywhere from 10 miles off the Florida coast to several miles northeast of the Bahamas. Right? We just don't know where it's going to be in that zone because we don't know how fast it's moving. But then, of course, we also have uncertainties with regard to the track. So even if we know exactly how fast the storm is going, we're not necessarily going to know where it's headed. And that's reflected in this cross-track spread, which reflects uncertainty in the path. So this is just one way of figuring out the uncertainties both in timing and in the actual path when it comes to the hurricane, because obviously the timing forecast is critically important for coastal residents trying to prepare for a storm. So that's one way of finding this uncertainty that's not necessarily obvious in those spaghetti maps.
So we're talking with Jack Sillen, one of the very smart people behind the weathermodels.com site, Dr. Ryan Maui from that site as well, and there are others, and Jack's been kind enough to come on today's broadcast of Hurricane U as we delve into the world of models. This could be, and it is, it's a college course. People they get degrees in this, and we're just going to spend a little over an hour on it, so it's very fascinating. So we appreciate Jack being here. That's who we're talking to today. All right, so let's move into, we've talked about, and let's just kind of refresh people as we jump into this next phase. Global models versus hurricane-specific models. If you could compare and contrast the two, please.
Yeah, so every different model that we run has a different job in mind, right? At the end of the day, these models are tools, and like any tool you have in your garage, each tool has a different purpose, right? So I'm not going to use the hammer to go cut something in half. I'm not going to use the saw to pound in a nail. And the same exact thing is true for weather models. They each are tools. They each specialize in different things, and trying to use one to accomplish the job designed to do by another is going to lead you down the wrong path. So with that in mind, we can take a look at the graphic that says different models have different purposes to get a better sense of this. And the idea behind a global model like the GFS or the ECMWF is to predict large-scale patterns across wide areas. So we talked about that trough over southern Quebec and that ridge over Newfoundland, right? That's what these global models are really designed to do, and they do it extraordinarily well. is they find the position of these large-scale features across the entire world.
Right.
They do that. They do an awesome job at that. But what they're not designed to do is predict very small-scale features. So you see that the rightmost plot here is the GFS forecast for the Sierra Nevada temperatures, and you can see that it's giving the general indication of colder temperatures at higher elevations, but there's really not much detail that you're getting here.
Gotcha.
And that's because the grid points in the GFS model are spaced 13 kilometers apart in space.
Oh, okay.
And the reason for that is that it's too computationally expensive to run it any higher. Right? I could run the GFS at 3 kilometers. There's nothing stopping me from doing that, except that I'd be able to give you tomorrow's forecast in a week, because that's how long it take the computer program to run. Now, that's not very helpful, is it? Right? So if we want to get a forecast, tomorrow's forecast, before tomorrow, we're going to need to make some compromises. And the compromise is to run it at a lower resolution so that it forecasts the big picture, right? It's telling you where it's going to be warmer than normal or colder than normal. It's telling you where these large-scale troughs and ridges are, but it's not going to give you the details. To give you the details, we need to run the model at a higher resolution. So the middle page is the 3 by 3 kilometer NAM model, which many of you are probably familiar with. And you can see that we start to get some more details about the mountain peaks and the various valleys that are going to have different temperatures. I didn't make a whole new graphic that's specific to hurricanes, but you could think of this, the hurricane equivalent as being the GFS model would tell you there's a hurricane over here somewhere.
Right.
The NAM model might be able to tell you here's where the eye wall is and the eye and the feeder bands. And then if you go over to the leftmost graphic, this is actually a model that we run in-house at weather.us. It's the 1 by 1 kilometer Swiss Super HD model, and it's going to give you the highest level of detail available, right? You can see every little canyon, every little ridge on the mountains. And the hurricane equivalent would be these will start to simulate your mesovortices within the eye wall. You'll get much better detail about the exact structure of the eye wall and the eye as it's moving ashore. These are obviously better for predicting these detailed features, but remember, there's a trade-off. We can't run these for the whole wide world, right? So the trade-off is that we're only running them for a very small area, which is usually, in the case of the hurricane-specific models like the HWRF, those models are only run for the immediate vicinity of the hurricane, including the hurricane itself. So you're not going to use it to get your forecast in Arizona during the middle of Hurricane Dorian. That you're going to have to rely on another model for. But it's basically trying to give us the best of both worlds, and it's saying that assuming that our global model did a perfect job predicting the large-scale pattern, how is a hurricane in its large-scale pattern going to behave? So it's important to remember that the HWRF's track forecast is really only as good as the GFS's track forecast.
That's what I was going to ask you.
That storm in the HWRF is going to be pushed by an upper-level ridge that's basically the same as whatever the GFS thinks. Now, that's not strictly true. The HWRF allows for some modification of near-storm features. So it's not saying it's the GFS verbatim until you're in the eye wall. There is some room for modification, and that's why the HWRF track forecast won't necessarily be the exact same as the GFS track forecast, but they're going to be subject to a lot of the same errors. So if the GFS makes a mistake, remember, if the GFS didn't expect those thunderstorms over Kansas City, the HWRF isn't going to expect those thunderstorms over Kansas City, and both of them are going to take Dorian west into Miami. But yeah, that's really, those are the two different jobs that they're designed to do. So and the HWRF is specialized in intensity forecasting, which remember we said we had to simulate those smaller scale processes to get the intensity forecast better. That's what the HWRF does a really good job at. It's not necessarily designed to be a track forecast model because we have the GFS and the Euro for those.
So when people say that the HWRF is run off of the GFS, that's what they mean when they say that.
Yeah. So it's nested inside the GFS is the more precise modeling term, which basically says that the HWRF is only run over a limited domain. But remember, we learned from those Kansas City thunderstorms that it's important to know what's happening even 1,000 miles away from the storm to forecast where it's going to go. And that's where the GFS comes in.
So why don't we have an HWRF that's run off the Euro?
So that comes down to politics, honestly, at the end of the day. Because, it's expensive to use ECMWS data. I'm not necessarily 100% sure why, for various reasons, that hasn't happened.
But it doesn't. That's the bottom line, right?
It doesn't.
Interesting.
Yeah, I know our Swiss HD model is run off the euro, but we pay through the roof to do that.
Wow.
And I think NOAA is trying to keep their modeling system consolidated. They're trying not to depend on the Europeans for their data needs. And honestly, the GFS is a really good model.
Right.
So there's no sense in spending a zillion dollars to run it inside the ECMWF when we can run it inside our own model and for a much lower cost and negligibly diminished skill.
So that's what I was going to ask you. Speaking of skill, when people talk about this battle between the Euro and the GFS, specifically talking about hurricanes, but even in general weather, what do we mean when we say that the skill? I mean, and we can just look at it in the graphic you sent me here, of course, is the 30-day running mean at the 500 millibar level. I call it millibar, you call it hectopascals. I'm just used to millibars. But, anomaly correlation 5-day forecast. So, the ECMWF seems to always be just slightly better than the GFS. What does that mean? Skill at what?
So, remember I talked about the output of these models is given as these strings of numbers, and they go on for a million years.
Right.
The skill happens when you compare the string of numbers outputted by the model to the string of numbers that you output from observations. And when those line up, you get 1 point. If they don't line up, you get 0 points, or you get a 0.9 if they're close, or
Right.
0.8 if they're a little less close. You do that for every single point, and for this plot, you're doing it for the 500 millibar forecast of the height at which your barometer might read 500 hectopascals
Right.
or millibars if you went up in the atmosphere over the entire northern hemisphere between 20 north and 80 north. So it's basically just saying that if you look at the whole forecast, the 5-day forecast for the pattern across the northern hemisphere, the ECMWF will be just slightly more skillful. It will make fewer errors. It will generate a forecast string of numbers that is ever so slightly closer to the real string of numbers if it were to be a perfect forecast. And it happens that the ECMWF is marginally better at that than the GFS over a long period of time.
And so we have the National Hurricane Center official annual average track errors. They publish this.
Oh, you cut out a little bit. I can't hear whatever you're saying.
Sorry. Now we're looking at the track errors from the National Hurricane Center. Am I still cutting out? All right, good. And so that's improved over time. And so how do they, I'm trying to figure out how to articulate this into a sensible question. So when you have all these different global models, is all of that taken into consideration, or is this just their forecast and how it's done? Somebody's got to go in and kind of keep score. Do we look at everything, the Canadian, the JMA, the Euro, the Swiss, the Icon, the GFS, the whatever? How much actually gets compiled to determine, quote, who's best?
So the graph that we're looking at here is the skill of the official National Hurricane Center forecast. So which models they use and don't use, you'll have to ask them.
Sure.
I have absolutely no idea. I suspect they use many of the leading models, so that would be the ECMWF, GFS,
right.
Perhaps the Canadian. I don't know what they use. But this is basically how their forecast pans out.
Right.
The map the graph that we looked at before, this anomaly correlation coefficient thing for the northern hemisphere, that's tabulated for every model that's run globally. So you're not going to see that forecast the HWRF, for example, appearing on that graph. Because remember, the HWRF isn't trying to predict anything over the whole northern hemisphere. It only cares about a very small area in which there might be a hurricane.
Gotcha.
So the scores are kept for every major global model. Tabulating them from the various meteorological agencies that run these models is not always easy. Some private companies run their own models, and they may not like we do. They may not be keen on sharing all that data with the rest of the world. So
Yeah,
sometimes it does
proprietary.
get hard to evaluate empirically exactly how skillful a given model is. But for most of the major ones, the data is kept, and even though it wasn't shown on that map, those values are available for folks who want to analyze it.
So what is the future of modeling? And I think the simple answer is maybe throw more money at it and have more computing power, but it's probably more complicated than that. And I mean, you talked about that there are some mathematical equations that are unsolvable that the world of computer numerical weather prediction scientists have run into, but does that mean we really can't improve beyond a certain threshold? Kind of like, well, we're never going to be able to go the speed of light, and so Han Solo jumping to light speed ain't happening. I thought anything was possible if you put your mind to it. That's what I was told.
Yeah. So with regards to so those are two different questions. One is there a predictability threshold?
Right.
And two is what are we trying to do to approach that if it exists? With regards to is there a predictability threshold? That's actually the subject of adamant and vigorous and super interesting scientific debate. So way back in the 60s, at least that's way back for me.
Me too. Yep.
A guy by the name of Edward Lorenz, the sort of father of chaos theory. He basically calculated that the limit of predictability for basically any sensible weather forecast, i.e. it's going to be sunny tomorrow or rainy tomorrow or whatever the case may be, it's going to be a hurricane tomorrow, is 2 weeks. You can't get any better than that.
Gotcha.
Now, he basically made that based on a series of assumptions about how chaos theory, remember that's the sort of the thunderstorm in Kansas City, is going to impact the track of the hurricane in Florida. He basically worked out that is a fundamental law of the universe, and with that constraint, we can never do better than 2 weeks.
Wow.
Since then, a lot of very smart people have argued, yeah, we can do better than 2 weeks. Maybe we can go 2.5 weeks, or maybe we can go 3 weeks for a sensible weather forecast. So far, no one's been able, at least to my knowledge, to offer a convincing argument that basically says that Lorenz's prediction won't hold up mathematically. If you look at the math, Lorenz's prediction is doing pretty darn well.
Yeah.
There is a case to be made that with advanced statistical techniques, so basically to say, with this ensemble approach, which is looking at the range of possible outcomes, can we extract useful information beyond the deterministic predictability threshold? So that's basically to say that if I were to look at one possible outcome, one model run, that may not give me any skill past 2 weeks.
Right.
But if I look at 50 of them and I analyze the trends, are more of them saying it's going to be 75 and sunny than 32 and snowing? All right, well, if 40 of them say 75 and sunny and 10 of them say 32 and snowing, then I'm going to side with 75 and sunny, and more often than not, I'm going to get it right. You can sort of do these workarounds to extract useful information beyond that 2-week horizon. And that's really, I think that's probably where the frontier of long-range weather prediction is going. I think in the short range, the next big milestone would be to run a model that's capable of resolving convection. So that would be 3-kilometer grid spacing across the whole world.
Oh, wow.
And so what happens if you were to run the GFS at the NAMS resolution? And that's a problem that you could solve with more computing resources. And I suspect that we'll get there within the next 5 to 10 years. We'll see a global convection allowing model. And I think that will both push the science forward and open up a whole new can of worms, because once you start to run models at that length or at that resolution, you can cross some problems off your list, but you add a whole lot more.
Yeah.
And a whole lot more of the problems that you're introducing are unsolvable.
Right.
You're replacing solvable problems with unsolvable problems, and it remains to be seen. Higher resolution isn't always equated to a more skillful forecast. So it's not just a matter of throwing more computing power into the mix. You also need to do, some tweaking. Remember those equations we talked about behind the scenes, sort of the middle step of numerical modeling?
Right.
You actually need to rewrite those equations if you want to run a model below 3 kilometers, at least a whole bunch of them.
Sure.
And we don't necessarily know what the best way to do that is yet. It's not quite as simple as throwing more money at it, though that really will help, as it always does. And we will eventually run into a you can't do better than this, or maybe we won't run into that, but we certainly will run into it's not economically feasible to do better than this, right?
Right.
At what point, if I can tell you within 10 miles where the hurricane's going to hit, I'm going to pack up, call it a day, and say, now I want to be able to predict within 10 miles for 2 days, or for 10 miles within 3 days.
Yeah.
So at a certain point, if we look at that Hurricane Center average track error, you see that the 24-hour track error is closing in under 50 miles. There very well may be a cost-benefit analysis that says it's more valuable for the emergency management community to have a more skillful, 120-hour forecast.
Right.
If we can bring that 120-hour forecast from 200 miles down to 100 miles, that's going to do a whole lot more good for the emergency management community than bringing the 24-hour forecast from 39 miles to 35 miles.
That's true. That's a very good way to look at that. That is. So that brings me to, I got 2 more questions for you.
All right.
That brings me to my next point here. So then what would be your advice for how people should ingest and appreciate all the model data that's out there? Because it is out there, and people will share 10-day Euro with a hurricane going right up Florida and whatever, and we've seen it. They do it with snowstorms. Oh my goodness, it gets wild, and it creates a lot of tension in the weather blogosphere. And so what would be your advice to the average person? And we're going to speak specifically to hurricanes here, but this is also, I think, applicable to a blizzard or another high impact weather event, severe weather. What should we as lay people take away from all this model guidance that's out there? How do we use it so that it becomes a tool in our toolkit?
Yeah, so here are a few guidelines that I think if you take away anything from this video, these are the things that I hope that you come away with this for anyone watching. The first I would say is throw out operational guidance past 5 days, right? Past 5 days, look at forecast model guidance, absolutely, but look at the ensembles, right? Because past 5 days, you're way more interested in the range of possible outcomes than any one given outcome, right? Okay. Remember that past 5 days, the odds of any one given modeled solution happening are really low.
Wow.
But the odds that the eventual solution will be included somewhere in that range of possible outcomes is really high.
Right.
So you can basically say the right answer is in here somewhere.
Yeah, we just don't know what it is. Right.
The ensembles, whereas you're almost certainly looking at the wrong answer if you look at the deterministic runs.
Wow.
So use ensembles past 5 days. Once you get inside 5 days, don't stick with any one specific model, right? So don't only look at the GFS or don't only look at the Euro. Create a sort of informal ensemble with all of them, right? Consider the Euro and the GFS to be just another ensemble member, and then look at the information that way. Always think in terms of the range of possible outcomes as opposed to this is what's going to happen, because you're really not going to get a this is what's going to happen until you're within 2 or 3 days, maybe, from the operational guidance. And then the next thing I would say is, I guess continuing on that theme, don't get too caught up in the details and don't expect models to do a job that they're not designed to do. So don't count on the GFS to resolve the maximum wind speed within a hurricane's eye wall. It's just not going to happen. There's going to be a number there, right? But if the GFS brings the hurricane over your house and says, all right, 122 mile an hour winds forecast, that actually doesn't mean very much because the GFS is not designed to predict the maximum wind speed inside the center of a hurricane. It's not designed to predict its minimum central pressure. Same thing with the ECMWF models. So don't use those global models to predict storm scale features such as the eye wall, or anything like that. It's not gonna lead you in the right direction. And remember that especially those global models are always going to start out over predicting the storm's minimum central pressure because they cannot physically resolve a lower pressure at the initial point. So remember those grid points that are every 13 kilometers apart, right? The GFS can't build a tropical cyclone of appropriate intensity out of there. So there's a lot of talk usually when the hurricane hunters are out in the storm and they record a minimum central pressure of say 920 millibars,
right?
And the GFS says, oh, it's the GFS's forecast for this point was only 960 millibars, so the storm is coming in way stronger than forecast. This is a huge problem. That's actually just an artifact of the GFS's inability to create a 920 millibar central pressure at that initial point. So keep that in mind. Use the models for their intended purpose, just as you would use a tool in your tool shed for its intended purpose. Stick to ensembles past 5 days. Create a poor man's ensemble, so to speak, with the global model guidance and the hurricane guidance within that, and don't expect any definitive answers until maybe 2 days out at the most.
Right, and I will add to it that the model guidance is out there. We all see it. It's not locked away, and it's not the official forecast. That the official forecast, you're going to learn about, and I talk about this a lot in my updates that I do on YouTube, that you want to get into what this means to the Hurricane Center forecasters. That's in the forecast discussion, and we're going to talk about National Hurricane Center products on an upcoming edition here. But please remember, as everyone's looking at these models, again, we will acknowledge they are out in the wild. We need to accept that they're not going to ever be reined back in, but don't let them replace the forecasters that are at the National Hurricane Center on a large scale down to what we call the WFOs, the weather forecast offices. Those are real people in there. At the bottom, it'll say Forecaster Blake or Forecaster Stewart, whatever the case may be. And these are real people. And the same thing holds true for your local area. At your WFO, your local National Weather Service office they have real people there. I know that the NOAA Weather Radio may be a synthesized voice now, but that's where the real forecast comes in. So the guidance is not the forecast. And people need to make sure they understand that. And I'll add to that real quick that use the model guidance sort of for your own amusement, your own entertainment, your own educational purposes. I like that one, right.
But if you need to make decisions about evacuation, if you need to make decisions about the protection of life and property, absolutely throw every model out the window and go for the Weather Service products.
Right.
They're going to be able to catch stuff that none of us are going to be able to see. Even the elite forecasters, they don't have access to some of the in-house stuff that NHC does, and they are the top shelf. They will always give you a more accurate forecast. Their errors that we've been talking about here, they might sound big, but they're lower than every single model. When we talk about looking at models and extracting useful information from models, this is really for your own sort of informational purposes, your own educational purposes. Absolutely do it, learn from it. Try to gain a better understanding of how the atmosphere works and how these powerful storms work. But when you need to put your money where your mouth is and make a decision that may impact your life or your property, absolutely always heed the guidance of the Weather Service and the Hurricane Center.
Right, because, acknowledging that it's out there, again, it's not going to be reined back in. I think it's a great thing that we have a society that's as educated as possible, that nobody owns the weather. And I see different people that get mad that people have access to this stuff. And yes, there are people that kind of either on impulse or maybe in some cases irresponsibly share a model, a deterministic usually. I mean, when has somebody ever shown necessarily an ensemble prediction and said, this is what's going to happen? It's usually some deterministic, dire outcome that gains 50,000 shares on social media. And that's the fringe side of this. But down the core, it is good. I think the more educated we are. I mean, look, we're going to all have. I said this last week. We're going to have honorary degrees in virology and epidemiology and exponential growth when this pandemic thing's done. Maybe, although this seems to change every day. But for real, it's good. It's out there. I like an educated audience because that helps me when I'm trying to talk to people. And then we boil it down. You say, look, those National Hurricane Center products on a national scale, if you will, your local products, and then your local news outlets, etc. We will talk about preparedness and Hurricane Center and Weather Service Office forecast products at a later date. So one thing, last question for you. This has bugged me for a long time, and I never understood what it meant. When somebody says, oh, the GFS is just suffering from convective feedback, what does that mean?
Yeah, so this is a very interesting problem. So remember, we talked about the grid spacing, right?
Right.
We always go back to that grid spacing. And there's 13 kilometers by 13 kilometers for the GFS. So what that means is that any feature that's not more than 13 kilometers across is invisible to the model. And what's something that's very important to the weather that's very often fewer than 13 kilometers across?
Right, thunderstorms. Yeah.
Right. So if you were to just run the model on its own, have it go on its merry way, it would never forecast thunderstorms, right? Because it would be incapable of generating them because it has no idea that these things called thunderstorms exist.
Wow.
So to solve that problem, we put in something called convective parameterization.
Okay.
And the convective parameterization is basically a computer program that says if there is sufficient instability, moisture, and lift, remember those are the three ingredients for thunderstorm formation, then we're going to do a manual override basically and say the GFS will predict thunderstorms in this area if there is sufficient moisture, instability, and lift. But remember, that's just an educated guess, right? It has no idea necessarily how strong those thunderstorms might be. Right. It'll guess, but it'll often guess wrong. And the problem is that those guesses are systematically high biased, or at least they were for a long time. We've gotten better at them now. But they were systematically high biased, which means that over and over again, these convective parameterization programs threw down a whole bunch of convection where there wasn't actually going to be convection that was nearly that strong. And what happens when that occurs is you get all this mass in the model, right? So all this air that is being moved up through the atmosphere in the updraft of these pretend thunderstorms, and then evicted out the top. And then you end up with a giant gaping hole in the atmosphere, and the GFS is all of a sudden saying, all right, an 860 millibar tropical cyclone, is that actually going to happen? No. Right. Is it happening in the model? Yes, because we're telling it that the thunderstorms associated with that hurricane are a whole heck of a lot stronger than they'll actually be.
Except sometimes we don't get an 860, luckily, but sometimes you get a Michael or a Dorian, and trying to decipher and figure out when is it. I know what you're saying, but that's real. So now we understand. So I see that a lot. That people will talk about it on message boards and on Twitter and elsewhere. Well, it suffers from convective feedback, and they throw these terms out there. And I honestly, till today, I didn't understand what that meant because I never stopped to, you know what, I need to email Jack or I need to email Ryan or Levi and ask them what this means because I've always been too busy when I see it. That's why we're here today. So thank you, Jack. I think we now all at least understand that a little bit better. Anything you want to add that we didn't talk about before we go?
I don't think so. I think we just about covered it from the basics of modeling, different types of models, the possible problems that arise with models, how we solve some of those problems, or at least attempt to pretend we solved them through ensembles, how to interpret some of those, some of the challenges associated with modeling hurricanes. I think we've just about covered it all. So thanks so much for having me on. This was a whole lot of fun, Mark. And feel free to reach out if you ever have questions about models and hurricanes and how it all works. And that goes for anyone watching too. You can find me on Twitter at Jack Sillen. And I really do try to get back to everyone who tweets me with a question. That's something I made a conscious effort to do, especially during Dorian. Right. Every time, every single person that would ping me with a question, either tweet me or put in the direct messages. I think I got back to every single person. So it was a lot of work, but I think that it's really important. If you have questions, I'm not sitting in the top of the ivory tower. I try to be as approachable as I can on social media, especially. So if you ever have questions about weather or weather models, feel free to reach out.
Well, Spider-Man's uncle, Peter Parker's uncle, said, with great power comes great responsibility, but it also leads to a great following. And the greater the following, the less time you start having. And so the two become contrasting. And so it not necessarily means that you're at the top of an ivory tower so much as it is you've got now 100,000 people following you and 9,000 people a day asking questions. It becomes very difficult, trust me. But I applaud that sense of, and I see others that do that. I really applaud that. And that's a great thing. Just be careful what you wish for, because as you grow, your time will become your most valuable commodity. You shall see. So one thing that I'm interested in, and hopefully we could do this, again, I'm just going to show this one more time. One of my favorite things that Jack does are these annotated maps that explain, with annotation, marking up, etc., what to expect going forward from that snapshot in time. Whether that snapshot is an ensemble prediction, scatter plot, or whatever you want to call it, spaghetti plot, or whatever the case may be. Jack does a great job of this, and especially after today and the success, I think, of how all this worked, I would love to be able to have you on as time permits. When you build one of those, that we actually go over it in real time, live, when we got a hurricane coming. And from the way things look, we might have a lot of hurricanes coming this year. So if time permits, I'd like to do this in the future operationally, as they say.
Oh, that'd be an awesome idea. Yeah, that'd be super fun. And definitely, if we have a hurricane out there in a couple months, give me a call, and I'd love to do that. That sounds like a lot of fun. Absolutely.
So, all right, folks. So let me just recap one more time. I want to make sure you know where to find Jack on social media, and of course, I will put the link to his Twitter, etc. I got to find it in here. There, come on. So Jack. It's real easy. Jack Sillen. There's not too many Sillens in the world, so he was able to get first. Of course, you signed up when you were 11, you told me, if you don't mind me divulging that.
Yeah.
So it was easy. But he's at Jack Sillen, S-I-L-N, S-I-L-L-I-N. And again, he's in college still, folks. Class of 22 coming up at Cornell. And just real quick, I know we got to go. I got to go. It's now 5:30. Have things been different for you? I mean, of course, this is rhetorical, but how are you handling things now? Was the semester close to being over? We're in this changed world. How has that affected you as a student?
Yeah, so I packed up everything from my dorm room in the dark of night back in mid-March. I had to make 3 trips to and from Maine, so that's 7 hours each way.
Yeah.
With the car full of all my stuff, trying to get it all out of there, and then set up shop back here in Maine, and now I'm doing everything virtually. So
yeah.
It's a little bit of a bummer. Obviously, there's great value in being able to go to class in person, being able to have conversations with peers and with professors,
right?
Sort of before and after class, but. Overall, everything has worked out about as darn well as it could. People have been really good about, recreating the class environment as much as possible. I consider myself really lucky, all things considered, how everything's worked out. I know there are folks who have had it much harder than I have. So,
well, we wish you the best of luck.
It's been a hassle, but
yeah.
All things considered, feeling very grateful for what we do have.
Rolling with it, doing the best we all can with this. Well, Jack, we appreciate your time very, very much. And remember, folks, this multi-part series we're going to eventually discuss. I'm working on lining up people. Hurricane preparedness, insurance. And again, like I said before, I know you're like, oh, insurance. Trust me. You want to know the ins and outs of insurance. There's a lot more to it than a boring insurance seminar. No, we won't make it boring at all. We'll do what we can, even if I have to bring a cat to help me keep your attention, or a kid. I'll bring one of my kids in here if I have to, and we'll make sure your attention stays on the insurance issue. We're going to delve into that. Insurance, National Hurricane Center products, how to make the best use of them. There's a lot of them now, a lot more than even when I started out more than 20 years ago. And very important, our local National Weather Service products, understanding hurricane local statements, that kind of thing, all over the next several weeks. And we will conclude this first round of Hurricane U by the time we're done with the month of May. And then it's going to be hurricane season. Get ready. All right. Thanks, everybody, for tuning in. I do appreciate it, as always, each week. This is supported by our patrons via Patreon, crowdfunding. It's what makes this possible. So a big thanks to them. I do need to figure out how to turn off the ads on the live stream, because I'm not monetizing it anymore, because we've got the Patreon support. So I'll figure all that out. And if you saw the very beginning of this, you'll understand exactly why. There was a little snafu there. But anyway, it's great to put this out there. I want to make it available for everybody with no commercials at all. And our patrons make that happen. So thank you all for supporting my work through Patreon. I am Mark Sudduth, HurricaneTrack.com. Thanks for tuning in to Hurricane U. I'll see you again next week.